So our next speaker is Scott Chapman from Sam Houston State University. Please.
Thank you, Mel. I appreciate it. And thank you for the very kind invitation to come in and join you. In the past, when I've come in, I've given some talks that dealt with numerical monoids and numerical semigroups. And if you like that material, then what I'm going to talk about today is kind of a logical next step to studying such objects, as these numerical monoids and numerical semigroups are additive submonoids in the natural numbers. We're going to jump up and look at additive submonoids of the rationals. And I'm going to start the talk by trying to point out why this might be interesting. I'm going to stick to the atomic property. There's a lot more in the literature over the last 3 or 4 years about factoring in these monoids, but I'm going to really stick to the basics today. For one reason, I think the basics are really interesting, and there's a very large problem in the basic material that I'd really like to see somebody answer, if not me and my co-authors here. But this is joint work with Felix Gotti and Marley Gotti. There, as I mentioned, there are several recent papers in the literature, and these 4 don't in any way, shape, or form cover everything that's there. But what I'm going to talk about today is covered in these papers. Number 1 is kind of a summary of 2, 3, and 4 that is in the current issue of the American Math Monthly. It's actually probably a little more technical than most of the papers you see in the monthly, but I think the people watching this talk would certainly enjoy it. There's 2 papers by Felix, one in Journal of Algebra, one in Journal of Algebra and its Applications, and a 4th paper by Felix and Marley that's in the semigroup forum. And everything I'm going to talk about here this morning in one shape or another is in one of these 4 papers. So, you know, I think whenever one kind of enters studying and anything algebraic, there's some reason that they do it. And I think for what I'm going to talk about today, there's a really, really good reason. And many of you might be familiar with this paper. P.M. Cohen's paper, Puiseux rings and their subrings. It's in the Proceedings of the Cambridge Philosophical Society before it was the Mathematical Proceedings of the Cambridge Philosophical Society in 1968. And I like to do this. I actually pulled this statement directly out of the paper. And if you look at that paper, one thing I find really interesting about it is if you then look at the direction in the 70s and the 80s that a lot of ideal theory took, this paper was very influential in that, with regard to that. In fact, it's been referenced well over 250 times. It's still being referenced today. And I'm going to pull a theorem out of it that's actually on the 2nd page of the paper. It says an element in an integral domain is called an atom if it's a non-unit which cannot be written as the product of 2 non-units. If every element of a ring R, which is not a unit or 0, can be written as a product of atoms, R is said to be atomic. The following result is easily verified. This is proposition 1.1. An integral domain is atomic if and only if it satisfies the maximum condition on principal ideals. And the paper contains no proof of this proposition. And there's a really good reason for that, because it's not correct. Now, before I say anything about this, I want to note that Cohen's maximum condition on principal ideals is equivalent to the ascending chain condition on principal ideals, or the ACCP. And so proposition 1.1 is incorrect. Cohen's correct that the left-hand implication is trivial to verify. The right-hand implication fails. In fact, the first example of an atomic integral domain without the ascending chain condition on principal ideals is in a paper by Anne Grams, which was about 6 years later in the math proceedings of the Cambridge Philosophical Society. Atomic rings in the ascending chain condition for principal ideals. And it's this example that I want to start looking at to lead us into why you might want to study Puiseux monoids. So here is Graham's example of an integral domain with ACC, without ACCP, which is atomic. Everything can be factored as a product of irreducibles. I'm going to start with a list of the ordered prime numbers. Pick any field F, and let M be the additive submonoid of the rational, of the non-negative rationals generated by these terms, 1 over 2 to the n times p to the n, where n ranges over the natural number. So that's an additive submonoid of the rationals. I'm going to let D be the monoid ring over F, determined by M, this monoid generated by these terms. And if I let big S be the elements out of D, which have a non-zero constant term, it's a multiplicatively closed set. Graham's example is this monoid ring localized at S. And I'm not overly concerned with tearing that ring apart. I'm concerned with M, the monoid generated by these elements, because it turns out, I'll make a couple of comments about M. If I let big B be this generating set, every element in B cannot be written as a linear combination over the non-negative integers of the remaining elements in B. So in the monoid M, each element in B is an atom, can't be factored. And remember, the operation here is addition, not multiplication. M is generated by its atoms, so it's what Cohen referred to as atomic. And if I look at this chain of principal monoid ideals, it's very easy to verify that it's an infinite ascending chain. It doesn't stabilize. So as a monoid, M does not satisfy the ascending chain condition on principal ideals. And if you get into Graham's example and tear it apart, you see that the factorization properties in M that I just went over play a key role. So there's some interesting things about looking at these Puiseux monoids. And I guess I should start by defining a Puiseux monoid. So Puiseux monoid is going to be any additive submonoid of the non-negative rationals. Now, I'm going to talk a little bit about when a Puiseux monoid is atomic, and I'll have one good result in that respect, and I'll have another, the non-result that I think needs a lot more study. But one interesting observation, which might puzzle your young students a little bit, there are uncountably many non-isomorphic Puiseux monoids. You know, one of these things, you start with this countable additive monoid, the non-negative rationals, and the Puiseux monoids turn out to be an uncountable class. To prove this, you use an old theorem of Fuchs, that there are uncountably many non-isomorphic rank 1 torsion-free abelian groups, and with a little bit of work, this result falls out. So there's a lot of Puiseux monoids. Okay, now, as I'm going to be talking about monoids the next couple of minutes, I just probably need to note that all these notions that Cohen was referring to with respect to rings carries over to monoids. If I have a commutative cancellative monoid, which all these Puiseux monoids are going to be, I'm going to call a non-unit irreducible if, whenever I write X as a sum, and again, the operation here is addition, even though I've written it here as multiplication. If I write X as the sum of two things, one of them has to be a unit. I'm going to let AM be the set of atoms of M. M is going to be atomic if it can be generated by its atoms, if every element can be written as a product of elements from this set A of M. And A is going to be antimatter if its set of atoms is empty. And I find this really interesting because in a beginning algebra course, you never talk about antimatter stuff. It's because antimatter stuff is a little bit hard to construct in the ring sense, but I'm going to show you there's a lot of monoids that are antimatter in a few minutes. Okay. Now, the monoid M in Grams's example was atomic, but not all Puiseux monoids are atomic. And let me start with a very simple one, which isn't atomic. And there's going to be no mystery in this argument. Pick your favorite prime number and let M be the Puiseux monoid generated by this infinite sequence, 1 over p to the k, where k is a natural number. And I'm going to use this kind of pointed bracket notation to illustrate generating sets for Puiseux monoids. M's not going to be atomic. In fact, none of these generators are atoms. Why? Like I said, this is simple because 1 over p to the k is p times 1 over p to the k plus 1. So again, you're using addition here. In fact, M has no atoms. It takes a little bit more argument to show this, but not a lot more. So this is what I'm going to call an antimatter monoid. It's a commutative cantilever monoid with no atomic elements at all. So obviously with no atoms. So obviously it can't be atomic. So again, the question I'll ask is, when is a Puiseux monoid atomic? So that's going to be question A. Now there's a lot of other questions we could ask here, and I'm going to touch on a few of them the next few minutes. When does a Puiseux monoid satisfy the ascending chain condition on principal ideals? If it does, it is atomic. That direction of the cone claim actually works. When's a Puiseux monoid antimatter? I'm going to show you a really nice class of antimatter Puiseux monoids in a few minutes. Given an atomic Puiseux monoid, what can we say about its factorization properties? I'm not going to go into great detail about that. There's a lot of papers you can look at if you're interested in those questions. In particular, there's been some papers about the length sets and the elasticities. As I said, I'm going to focus on A. I'm going to talk a little bit about B and C, and unlike what the slide says, I'm going to kind of slide over D. So again, I think there's a really good parallel to be drawn here between the Puiseux monoids I'm talking about and the numerical monoids, the submonoids, and the natural numbers. And here's a little chart to kind of compare the two types of monoids. And everything about a numerical monoid is nice until you start trying to compute its Frobenius number, which I'm not going to get into. But numerical monoids are always finitely generated. They're always atomic. They always satisfy the ACCP. They're never antimatter. And if you like to investigate factorization invariance, numerical monoids, this has been done to an extreme. You can spend a lot of time in the literature looking at papers on this. But Puiseux monoids are very different. They may not be finitely generated, as we've already seen. We've already seen they might not be atomic. They may not satisfy the ACCP. We've already seen that. They may be antimatter. I've already looked at one of those. And there's not much known about their factorization properties. There's a couple of recent papers. So this is kind of an area where there could be a lot more work done. And I know Felix and Marley are doing a lot of this work. It's easy to determine, and one of the reasons I did stop with the previous slide and look at this comparison is it's easy to determine which Puiseux monoids behave like numerical monoids. And this is not hard to prove. A Puiseux monoid is isomorphic to a numerical monoid if and only if it's finitely generated. So if you're a Puiseux monoid and you're finitely generated, you're isomorphic to a numerical monoid, and all the things on the left-hand side of that chart on the previous slide are going to work. So those aren't what I would call the interesting Puiseux monoids. So if a Puiseux monoid is finitely generated, again, using the chart on the previous page, it has a unique minimal generating set. It's atomic. Its atoms are precisely the elements of this generating set, and it satisfies the ACCP. Now, the first thing I'm going to do is when I focus on the non-finitely generated case is I'm going to slightly extend the last three ideas into a proposition that works for all Puiseux monoids, finitely generated or non-finitely generated. So for a Puiseux monoid, the following conditions are equivalent. M has a minimal set of generators. M has a unique minimal set of generators, and M is atomic. So let me illustrate this proposition with kind of a example, which builds on the Graham's example. What I'm going to do this time is I'm going to build a different generating set. I'm going to let S be the set of all reciprocals of powers of 2. And let's stick with this set P of the ordered list of odd primes. So let's let M be the Puiseux monoid generated by the union of these two sets. Now, I actually, there's a typo. P is the set of odd primes. I'm not going to look at S union P. I'm going to look at S union, the set of reciprocals of the primes. So there's my first big typographical error. So each 1 over P sub n, you can argue that it's an atom. But as with the argument before, no 1 over 2 to the n can be written as a sum of atoms. So M is not non-atomic, but it still has infinitely many atoms. So what's the trick here is the reason that it's not atomic is that the generating set, S union, the reciprocals of 1 over the odd primes, is not a minimal generating set. You could throw out a lot of these 1 over 2 to the n's and you'd still have a valid generating set. And it's not hard to argue you can't build a minimal one either. So this example would not be atomic. Okay, now here's probably the best result I have. It doesn't have an overly difficult proof. It takes about 3/4 of a page to prove this. But if you have a Puiseux monoid, if 0 is not a limit point of M, then M is atomic. And as I'm saying here, the proof is straightforward. Assume that M is not atomic and you construct a sequence of elements which converges to 0. So again, this is not too difficult to see. And we note that Graham's example shows that the converse does not hold. Graham's example does have 0 as a limit point, and it's not atomic. So when 0 is a limit point, there's not much that can be said in general right now about the atomic property. The atomicity of this subclass of Puiseux monoids is very complex, and it's not understood real well. And I'm going to try to illustrate this with some additional examples. So here's a really nice class of Puiseux monoids. It's actually a class of semirings, which when you look in the literature, this is where you see these things, or what you see these things referred to as. So if R is a positive rational, just look at the Puiseux monoid generated by all its non-negative powers. So I'm going to call this the cyclic semiring generated by R. I'm only going to look at the additive structure. If you want to, you could also consider its multiplicative structure, but I'm going to stick to the additive structure. And we can completely describe the atomic structure of these cyclic semirings. So if I write R as A over B with A over B relatively prime, I'm going to let N of R be the numerator and D of R be the denominator. So first of all, if you pick an R which is bigger than or equal to 1, then R is atomic. Obviously, it's not going to have a 0 as a limit point. And if R is a natural number, then S of R is going to be isomorphic to the natural numbers. And if R is not a natural number, then the atoms just turn out to be the powers that generate it. Now, if R is less than 1, if the numerator is 1, then SR is antimatter. And if the numerator isn't 1, then SR is atomic with the same set of atoms as what you used in number 1. And the proof of this is not too difficult. The antimatter part gets to be a little bit more complicated, but this is a really well understood class of Puiseux monoids. And using this result, you get a nice, what I think is a nice set of objects, which it would be a good way to introduce students, even beginning graduate students, to this notion of things that don't satisfy the ascending chain condition. Pick an R between 0 and 1, a rational, with numerator not 1, then you get an atomic monoid that does not satisfy the ACCP. So you get kind of a simpler object than this thing that Graham's constructed. And here's the proof. I just wanted to show you the proof is not difficult, but keep in mind that you're doing things here in the additive sense and not the multiplicative sense. So if you want to take a look at the proof, there it is. It's very, very straightforward. So now to finish, let me say a little bit about antimatter things. So if I'm given a Puiseux monoid, let's look at what you would call the quotient group. You can define it very simply as the differences between all the elements. It's a subgroup of the rationals. And if you're a commutative algebraist, this is an object that's not surprising to pop up here. I'm going to call it M tilde. It's essentially what we call the root closure of M in the group. So it's the elements in the group that some multiple of that element winds up back in the monoid M. And this is a really nice exercise. Given a Puiseux monoid, you can write its root closure down fairly easily. And here it is. If M's a Puiseux monoid and N is the greatest common divisor of the numerators of the elements in M, then the root closure is N times the Puiseux monoid generated by 1 over the denominators in M. So it's in some cases an infinitely generated Puiseux monoid. And let me close with a result about the root closure. A Puiseux monoid is not finitely generated if and only if its root closure is antimatter. So you now have a machine that will spit out antimatter monoids really quickly. And again, I don't know if you've ever thought about this. When I first started studying these things, the antimatter idea really disturbed me. But now there's an easy way to approach it with this result. And let me close with a nice antimatter monoid constructed using this proposition. So take the set of prime numbers and let's look at a really natural Puiseux monoid. The monoid generated by the reciprocals of all the primes. So 0 is a limit point, so it's not finitely generated. So by the proposition, the root closure of this thing's antimatter. And if you go through the construction on the previous slide, it turns out here's what the root closure looks like. It's the Puiseux monoid generated by 1 over N, where N's square free. So that Puiseux monoid turns out to be antimatter. And trying to argue that directly is not overly simple. So I'm going to close with that, and I hope maybe I did a couple of things that you thought were interesting, and it might make you go back and look at this material a little bit more. And if there are any questions, I will be glad to try to answer them. And let me again thank Mel for the kind invitation. And I will close off and answer any questions.
Thank you very much, Scott. Are there any questions?
It doesn't look like it.
Well, I have to say, I thought it was fantastically interesting because people have studied numerical semigroups, these monoids in the natural numbers, for aleph naught years. But the idea of looking at these essentially numerical semigroups for the positive rationals, that's really something where I can see a lot of future development. I mean, that's really cool.
I agree. And again, if you did take a lot of interest in this, that monthly paper is a good place to start. But Felix and Marley have written, multiple papers on this. And I actually think this question that I raised is a really good one. If you have a Puiseux monoid that has 0 as a limit point, when is it atomic? Felix has addressed this in several papers. It's not an easy question, and maybe some people watching this talk might get interested in it.
I just wanted to make one bibliographical point, which is you mentioned the mathematician P.M. Cohn,
Yeah.
but it is C-O-H-N, not C-O-H-E-N.
Oh, so I goofed. So you can blame me.
Yeah, no, but
Yeah.
I mean, because he is like one of the great guys in non-commutative algebra. But
You know, absolutely. And that paper was one of the first papers I ever read. That 1968 paper where there's the unfortunate error. But yeah. So thank you for the correction. I will fix that if I ever give this talk again.
Comments or questions? If not, I thank Scott again for a really interesting talk. And the next talk is Paul Baginski in 5 minutes.
Thank you.